The equations of motion of the last lesson refer to the fixed frame, but the simplest relation between angular momentum and angular velocity holds in the moving frame along the principal axis. So we first transform them to the moving coordinates. One rule covers any vector. If the vector does not change in the moving frame, its rate of change in the fixed frame comes purely from the rotation and equals the cross product of the angular velocity with it. In general, we add its own rate in the moving frame. Applying that rule to the momentum and the angular momentum, the two equations of motion become the rate of change in the moving frame plus the cross product of the angular velocity with that vector equals the force or the torque. Taking components of the first, with the momentum written as mass times velocity, gives three equations. Each carries a product of one angular velocity component with one velocity component, which is exactly what the cross product contributes. The second is prettiest in the principal axis, where each component of the angular momentum is a principal moment times the matching component of the angular velocity. Substituting gives Euler's equations, whose product terms come from that cross product. With no external torque, the right-hand sides vanish, and the three equations involve only the angular velocity. The components stay coupled. The rate of change of any one is set by the product of the other two. Try a symmetrical top. The two transverse principal moments are equal, so the product term in the third equation drops out, and the component of the angular velocity along the symmetry axis is constant. The remaining two become a simple coupled pair. The rate of the first component is minus a frequency times the second, and the rate of the second is that frequency times the first. The frequency is set by the axial component and the difference of the moments. The solution is a uniform rotation. The first component is an amplitude times a cosine, the second the same amplitude times a sine. So the part of the angular velocity across the symmetry axis keeps a fixed magnitude and turns about that axis at this frequency. Since the axial component is constant too, in the frame turning with the body, the angular velocity keeps its magnitude and rotates uniformly about the body's own symmetry axis, and so does the angular momentum. It is the regular precession seen from the body.